Hello everyone, I am Vaishnavi. Emertxe Information Technologies has provided us with an embedded systems internship where we are learning embedded system concepts through microcontroller simulation. This internship is helping us understand how embedded systems work in real-time applications. My team members are Cheripelli Saivamshi, Dadipelli Himabindu, Antati Akila, Lattipelli Vaishnavi. We are students of Sri Hindu College of Engineering and Technology in Electronics and Communication Engineering. As part of this internship, we are a group of students working together on this project. Each team member contributes to different parts of the project, such as learning concepts, coding, simulation, testing, and documentation. Working as a team has helped us improve our communication skills, coordination, and problem solving ability. During this internship, we learned these concepts. Internship overview, C programming fundamentals, introduction to embedded systems, elements of an embedded system, types of embedded systems, microcontroller versus microprocessor, peripheral interfacing, LED interfacing, CLCD interfacing, matrix keypad, timer and interrupts, project overview, microwave oven simulation, and conclusion. Started with C fundamentals. C programming is called a middle level language. It supports both high level programming and low level hardware control. Because of this feature, C is widely used in embedded systems. It allows direct communication with hardware components. C provides different data types to store values. The int data type is used to store integer numbers and occupies 4 bytes. The char data type stores single characters and uses 1 byte of memory. The float data type stores decimal values with single precision. The double data type stores decimal values with double precisions. Basic operations. C language provides the basic operations to perform calculations and decisions. They are arithmetic operators, logical operators, bitwise operators, and ternary operators. Arithmetic operators are used for mathematical operations. Operators like plus, minus, multiply, and divide perform the calculations. The modulus operator is used to find the remainder. Increment operators increase a variable value by 1. Pre-increment updates the value before it is used. Post increment updates the value after it is used. Relational operators are used to compare two values. These operators return true or false results. Conditional constructs help in decision making. Loops are used to repeat a set of statements. The while loop checks the condition before execution. The do while loop executes the code at least once. Jump statements like break and continue control loop flow. And next, logical operators are used to combine or modify conditions in C. And or not operators are represented by symbols. These operators follow the concept of short circuit evaluation. In OR operation, if the first condition is true, the second is skipped. In AND operation, if the first condition is false, the second is skipped. Bitwise operators work directly on binary bits of data. Bit level operations, left shift and right shift operators move bits to left or right. The ternary operator provides a short way to write if else conditions. Arrays are store multiple elements of the same data type in continuous memory. Next will be continued by my friend Bindu.
Alright, now let's define what an embedded system actually is. It is a computing device designed to perform a specific dedicated task, unlike a general purpose computer like a laptop, which can run thousands of different applications. An embedded system is built to do one job perfectly. It combines hardware sequentially, microcontroller, with software to control a device or machine. There are three main characteristics to make a system embedded. First is dedicated functionality. It focuses on a single task like controlling an AC unit. Second is resource constrained. To keep cost low and efficiency high, we work with limited memory and processing power. Unlike the gigabytes of RAM in a PC, we often work with just kilobytes. And third one is real-time operation. In many embedded systems, time is critical. The system must respond to an input immediately. For example, in microwave project, the timer must stop exactly when it hits zero. A delay is not acceptable. An embedded system is made up of several basic components that work together. First is the system core. This is usually a microcontroller or microprocessor. It acts as the brain and controls all operations. Next is memory. Memory stores the program and data. It includes RAM for temporary data and ROM flash for program storage. Then we have two input ports. These receive data from sensors, switches, or keyboards. Output port sends result to device like LEDs, motors, displays, or buzzers. Finally, other devices include timer, ADC, communication modules, etc. All these blocks together form an embedded system. Embedded system can be classified into different types based on how they operate and where they are used. First one is standalone embedded system. These systems work independently without needing a network. They take input, process it, and give output. Example, washing machine and microwave oven. And the second one is real-time embedded system. The system must respond within a fixed time limit. Delay is not acceptable. Example, airbag systems. And the third one is networked embedded system. These systems are connected to a network. They can send and receive data. Examples, mobile phones and IoT devices. And the fourth one is mobile embedded system. These systems are used in portable devices. They run on batteries. Example, smartphones. And the fifth one is hybrid embedded system. These systems combine features of more than one type. Example, a smart car systems. We look at the heart of our system. It is important to distinguish between a microprocessor and microcontroller. Think of microprocessor as a very powerful brain that needs external organs like external memory and input output chips to survive. These are found in our PCs and are great for high speed multitasking, but they are expensive and consumes a lot of power. On the other hand, a microcontroller like PIC 16 F877A we use it is like a system on chip. It has the brain, the memory and the communication ports all in one small and inexpensive package. Because of our microwave oven has a specific dedicated task. The microcontroller is the perfect choice. It is very little power, takes up almost no space on the circuit board, and provides exactly the amount of processing power we need to manage our timers and user interfaces. And next will be continued by my friend Akila.
PIC 16 F877A microcontroller. The PIC16 F877 is an 8-bit microcontroller that follows hardware architecture, which means it uses separate buses for program instructions and data. This improves processing speed and efficiency. It can operate at a clock frequency of up to 20 MHz, making it suitable for many embedded applications. The microcontroller has three types of memory. It contains 8K words of flash program memory for storing the program, 368 bytes of SRAM for temporary data storage,
and 256 bytes of EEE for storing data permanently even power is off. PIC 16 F877A provides 5 input output ports, named port A to port E, offering a total of 33 input output pins. These pins can be used to connect external devices like LEDs, sensors, and switches. It also includes important peripherals such as timers, interrupt system, and digital input output features, which help in controlling and monitoring external hardware. This is the block diagram of PIC 16 F877A and also pin diagram. Peripheral interfacing. Peripheral interfacing connects external devices like LED switches, fans, and buzzers to the microcontroller. For output devices, the TRIS register is set to 0 to make the pin act as an output. The port register is then used to send either high or low signals. LEDs and actuators respond based on the logic level given at the port pin. In the project, RC2 controls the fan and RC1 controls the buzzer. For input devices, the TRIS register is set to 1 to configure pins as inputs. Switches provide input signals to the microcontroller through these pins. Pull-up registers are required to avoid undefined or floating input values. Internal pull-up resistors are enabled on port P for stable inputs. The setup is used to read the column signals from a matrix keypad. The CLCD is connected to a microcontroller to present system information clearly. It displays the current status and timing details of the system. The selected cooking mode is shown on the LCD screen. It indicates both the preset time and the ongoing operating time. The display works by receiving command and data instructions from the controller. Specific control signals are used to manage the display functions. Proper initialization is required before any information is displayed. Initialization ensures accurate and stable output on the screen. The CLCD mainly operates in write mode during operation. This allows continuous real-time updates of information. Matrix keypad. A matrix keypad is used an input device in embedded systems. It allows users to select operating modes and set time values. The keypad is connected to the system through GPIO input pins. Keys are arranged in the form of rows and columns. Key detection is done using the row column scanning technique. When a key is pressed, the corresponding row and column are identified. It supports level triggered key detection. It also supports state triggered key detection. The keypad makes menu navigation simple and efficient. Overall, it improves user interaction and control in the system. Timers and interrupts. Timers are used to create delays and measure elapsed time. They help the system keep track of timing accurately. Timer interrupts triggers actions at specific time intervals. These interrupts allow precise control of time-based service routine updates time-related operations. The ISR works without stopping the main program execution. This parallel operation makes the system faster and smoother. Timers reduce CPU workload by automating time management. Interrupts improve overall system performance and response time. Timers and interrupts are vital for real-time embedded systems. The next part will be continued by my teammate Sai Vamsi.
Let's discuss about the core objective of our project. It was to create a reliable simulation of microwave oven using the PIC16F877A microcontroller. We didn't want just to blink the LEDs. We want to replicate the actual user experience of kitchen applications with user-friendly interface using 16 into 4 CLCD display and 4 into 3 matrix keypad. These involved managing multiple cooking modes, handling users' input for time and temperature, and ensuring the safety and accuracy of countdown timer. There are four modes: micro mode, grill mode, convention mode, start mode. The micro mode is the standard mode for cooking. The user defined power 900 watts and the timer Second is the grill mode. Grill mode is the special mode, highly heated simulation for grilling the task, which grilling and browning the food. Then the grill mode is similar to micro mode with special tasks. The convection mode, it is a complex mode which involves predefined temperature setting up to 250 degrees Celsius and preheating cycle. After this, the timer will be allowed to set the user. The fourth one is the start mode. It is a one touch button to start the 30 seconds cooking cycle. The entire system was developed with embedded C using the MP Lab X micro environment. Since we were working with simulation environment, PixMLab allowed us to verify our code on virtual PixGenio board, ensuring that our registers configuration for keypad and LCD were industrially accurate. We used XC8 compiler PixMLab. Let's see the demo of our project. First, we have to load the hex file. This is the power on menu. There are shows It shows four modes: micro mode, grill mode, convection mode, and start mode. When we are starting with micro mode, which takes default 900 volts. The timer will start to set. When we want to stop the timer, we can pause the fifth bit with fifth button. We can resume it with fourth button. We can stop it with sixth button by pressing sixth button.
Next is the grill mode. When we press second key, it will enter to grill mode, which similar to micro mode, but this mode is used for grilling and browning food, which internally follows same timer and fan control. First we have to set the timer to 15 seconds.
Convention mode. By pressing start key, it enters into convention mode. The convention mode is the most logic heavy part of the project. Unlike the other models, it requires a temperature input first. So that it does means first we have to set the temperature at 140 degrees Celsius. After setting temperature, the system goes into preheating mode. This means the oven is getting ready and heating up. We programmed a specific 180 seconds countdown that simulate the oven reaching the desired temperature. During this phase, the user cannot set the cooking time. The system effectively blocks the next step will the preheating is completed. This demonstrates how we manage sequentially dependency in an embedded system.
Start mode. Start mode is activated by pressing 4 from the main menu. System is automatically selected to 30 seconds. Fan and timer to start immediately. If 4 is pressed during cooking, 30 seconds is added to current timer. Conclusion. This internship provided a deep dive into register level programming and the development lifecycle of an embedded system, from initial hardware configuration to final system simulation. The implementation of the microwave oven simulation demonstrates the effective use of a PIC16F877A microcontroller to manage real-time hardware-software synchronization in a resource-constrained environment. Thank you.